I mean, I know this is the AI group, and I'm basically trying to present this work in a context which I'm hoping will be relevant to AI considerations. And I mean, the broader question is, can a fallacy be rational, right? And in psychology, in behavioral economics, decision theory, most of these areas, the predominant framework for probabilistic inference is basically classical probability theory, Bayesian theory, and people love it. It is a predominant framework for a good reason. There is this formal a priori motivation. You may have come across the Dutch book theorem. It's excellent descriptive coverage on the whole, and of course, it's very intuitive. And especially when it comes to trying to model human decision making, it makes sense to employ principles which appear to us intuitive, because after all, we're trying to model human intuition, right? So in terms of modeling human intuition, it makes sense to use principles which appear intuitive. The problems with Bayesian models is that they scale poorly. And of course, if you're a computer scientist, perhaps you're a bit more aware of these problems than the average psychologist. But essentially, if you're trying to be a Bayesian reasoner and you have n questions with k options each, the number of terms needed in the joint probability distribution scales up exponentially. So it just to be a full rational Bayesian is just not possible for realistic problems. Now, in the kind of more advanced Bayesian psychologists do acknowledge this problem, and they employ a number of approaches to deal with it. And these approaches are basically sampling approximations. So instead of computing the full joint probability distribution in all its horrendous glory, they just sample terms, like, for example, Markov Monte Carlo Markov chain approaches, MCMC, and things of that sort, or particle filtering. And in this way, they try to basically say, well, the brain tries to be a full Bayesian rational, but in actual practice for many realistic problems, it uses sampling approximations. So that's kind of the established wisdom in terms of cognitive science and decision sciences. What I'm going to do is try to present to you an alternative possibility for how to deal with the intractability of classical probability distributions. Now, in order to motivate this alternative approach, I'll just go through some of the findings which are more commonly invoked to illustrate the discrepancy between Bayesian prescription and human reasoning. From an artificial intelligence perspective, this is relevant in the sense that, well, if we want to mimic human decision-making as closely as possible, then, well, we need to be aware that humans are prone to these apparent mistakes. So I'm kind of going to spend a little bit of time talking about some decision results, and then I'll describe the way we propose to deal with Bayesian intractability. And then, by that time, hopefully I will have finished as well, so you can ask questions. But just like the broad picture of what I'm trying to talk about tonight is, we start with the premise that Bayesian theory is the assumed rational approach in probabilistic inference for human agents, AI agents as well. But of course, full Bayesian inference is not possible. Then I'll show some results which are particularly striking discrepancies between Bayesian prescription and what humans do. And then I'll try to explain how we're trying to deal with these issues with this alternative approach we've been developing based on quantum theory. Okay, so let me talk about a couple of fallacies, right? And these fallacies essentially illustrate for many people, these fallacies illustrate that whatever human decision-making is about, proper Bayesian theory can't be the whole story. And you may have come across this example. It's from Tversky and Kahneman in 1983. It may seem a while back, 40 years ago. Nonetheless, it is arguably, this is the single most famous decision finding in all of decision literature. So if you've not come across it before, it's a good opportunity to kind of like consider it for a bit. And these guys also are not random guys. You may have come across Kahneman. He got a Nobel Prize in economics for prospect theory, which he co-developed with Tversky. Tversky is, I think, is the highest psychologist of all time. So the example may seem to be a little bit simple if you're not familiar with decision research, but nonetheless, you know, it has a very sort of illustrious history and background. Okay, so remember we are in 1983, so please excuse these very out-of-date stereotypes about gender stereotypes. Participants received this paragraph about a hypothetical person, Linda. So Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Participants were given a list of statements about Linda, and they were asked to rank order the statements in terms of least likely to most likely. We can sort of simplify here. And the question is, which is more probable? And the two key statements were, Linda is a bank teller, and Linda is a bank teller and active in the feminist movement. Now, of course, the description for Linda makes her very unlikely to be doing a slightly boring and exciting job, such as being a bank teller, right? Most people rate this first possibility very low. But the conjunction seems to make a bit more sense because, well, Linda was described to look very much like a feminist in 1983. So again, you know, just please bear that in mind that it was four decades ago. The most established, the kind of widely replicated finding is that more participants choose the second option, that the conjunction has been more probable than the first one. Of course, if you're mathematically oriented, right, you know, it's immediately clear that conjunction can never be more probable than the marginal. So that's a fallacy. And the reason why it's this result has been so famous in decision theory is because, on the one hand, it's an obvious error, and I'll illustrate that shortly again. On the other hand, somehow intuitively, it just seems a little bit more likely to say about Linda that she's a bank teller and a feminist rather than just a bank teller. So it's this kind of discrepancy between what humans consider reasonable and intuitive and what Bayesian theory tells us that kind of like underwrites the importance of this finding. Okay, you know, again, if you're not familiar with decision theory, you can think of all sorts of objections to this result. You know, maybe participants understand the conjunction as a conditional. Maybe they understand Linda as a bank teller as something different. There have been like literally hundreds of studies looking at various methodological or other empirical manipulations. The result is very robust. If you have any questions about it, I'm more than happy to answer them. I love talking about the conjunction fallacy. So, you know, if you have any questions, you'll have to stop me eventually. But anyway, the conjunction fallacy is a well-established finding. Just to kind of illustrate the point, perhaps less necessary for this audience, but nonetheless, the problem is that you can imagine a sample space of all possible Lindas. And in that sample space, of course, you're going to have very many feminists, because the description for Linda made it very likely she's a feminist, and very few bank tellers for the same reason. Of course, a conjunction can never be more likely than either marginal. Now, the conjunction fallacy. So you know, it's possible. I mean, the most common objection to the conjunction fallacy finding, as I just described it, is that people perhaps don't quite get the set theoretic structure of the problem right. They just do something different. They don't use probabilities. Maybe they use heuristics. Maybe they use something different, right? But it's conjunction fallacy has been demonstrated with problems which make the set theoretic structure of probabilities extremely obvious. So, for example, this very well-known study by Tentori colleagues, participants were told that it is common in the Scandinavian peninsula to come across people with both blue hair and blue eyes, right? Blonde hair and blue eyes. I keep meaning to correct that and I forget. Now, imagine such a person chosen at random and choose the most probable between the following three statements. The individual has blonde hair. The individual has blonde hair and blue eyes. The individual has blonde hair and does not have blue eyes. Again, we're talking about Scandinavian individuals, right? We can't think it's likely they'll have blonde hair, it's likely they'll have blue eyes. But of course, said theoretically, it's not possible to have more individuals with blonde hair and blue eyes than just blonde hair. But that's exactly what people do. The conjunction, again, is rated as more likely than the marginal. Now, in such a problem, you can just imagine, your participants, your agents, just kind of lining up all our Scandinavian individuals, and you just can't have more in the conjunction than in the marginal. It is really a shocking result that participants make this error. It's even more shocking that even people who understand set theory and probabilities and all these things, like ourselves, still can somehow consider the conjunction as just a little bit more likely than the marginal. It's just weird. So, in trying to understand, I guess, the connection with artificial intelligence is, if we try to understand what should be our principles for probabilistic inference in artificial intelligence. Well, if our starting point is that these principles should be like whatever it is the brain is doing, because the brain seems to be successful in all sorts of ways, well, just baseline Bayesian theory seems not quite to do it. And that is kind of, as you can probably tell, I love this kind of work simply because it just shocks people with a formal background just to such a fundamental degree. Okay, so there are several examples like this. I'm not going to take, I'll only take a few overheads to just illustrate, in part because I think they're amusing. So another well-known conjunction fallacy is that the probability that one has had one or more heart attacks and is older than 55 is rated as more likely than the probability that the person has had one or more heart attacks. Again, if you're a full Bayesian, well, you can't do that. The probability that cigarette attacks will increase and teenage smoking will decrease greater than the probability that teenage smoking will decrease. Of course, you can see the trick in terms of how these people are trying to set up this conjunction fallacies, right? They just throw in a very strong causal connection between the two predicates in the conjunction. But again, I mean, if your system is using Bayesian theory, it doesn't matter if there's a strong causal connection. The conjunction needs to respect the set theoretic constraints and not be more likely than the marginal. Okay, so let me show you, let me just kind of like offer two more examples of these probabilistic fallacies. Because again, these kind of examples underwrite our expectation that something as seemingly irrational as Bayesian theory is, at least in its baseline instantiation, a good basis for understanding either human or artificial intelligence. Now, that example is particularly topical because obviously, we've had stressful elections, referendums, all sorts of things, right? And of course, very often, people who are on the edge, people who are unsure about which way to vote or what to do, well, they'll use Gallup polls to be guided. Now, you just excuse me for just 1 second because there is someone at the door, and I think my people are just okay. So okay, all right. So these these results are from an actual Gallup poll, and they were basically conducted with a proper sample, with a large sample of about 1,000 participants in the context of an actual Gallup poll in relation to American politics about 2 decades ago, right? And there were 2 questions. They weren't presented together, right? They presented one after the other. Is Clinton honest? And the yes proportion to this question was 50%. Is Gore honest? The yes proportion was 68%. Now, we can see the logic in these answers, right? There's nothing surprising. But when you switch the order, actually the probability for yes to Gore rises to 6%. The probability for yes to Clinton drops to 57%. Again, given the importance of Gallup polls in public opinion, that's a shocking difference. You basically, Clinton's honesty increases by nearly 20% if it comes after a Gore question. obviously, I mean, behavioral scientists are well aware of these biases, right? And they, they sometimes can exploit them in terms of like setting up these questionnaires. The point remains that you can't, you just can't take for granted simple constraints from Bayesian theory. Okay, just very simply, the classical theory view is if A is probability to answer yes to question A and B the probability to answer yes to question B, then probability of yes to A and then yes to B is just that. So probability A, right? And then probability B given A, because we've just seen A. Of course, that's a conjunction. Conjunction is commutative. You can flip it. You predict no order effects. So according to our beloved Bayesian theory, there should be, we should have the same pattern of answers, whether we have Clinton honest and then Gore, or the other way around. Empirically, we don't see that. Now, medical diagnosis is very much in all our minds these days for the last year. And next time you go to the doctor, you might be interested in this result with actual medical trainees as participants. So, so these medical trainees were asked to estimate the probability of an infection given information about a lab test and a physical exam in a certain order, which is 0.59, versus the same information presented in a different order. Again, you see a difference in probability of about 20%. With a Gallup poll or with a conjunction fallacy, you might be inclined to say, well, actually, these are instances of probabilistic inference where people don't really care so much about the decision. In this case, though, the decision is a high stakes one, and there is a very, very high expectation that, if a rational decision making occurs in many aspects of human cognition, it is when it comes to medical diagnosis. So anyway, again, just to kind of recap quickly, if you believe CP theory, then probability of a hypothesis given a conjunction of evidence in one order should be the same as the other way around. Okay, so I'm not going to go through that. I mean, it should be obvious, and I'd rather spend a bit more time talking about the quantum. Okay, so it has to be said that even though, of course, commutativity in conjunction is highly intuitive, right? But also, at least in decision theory, there's been a lot of work arguing that actually it can't make sense to have this order effects because the first question possibly activates perspectives or mindsets that alter the way we approach the second question. And from such a point of view, you would expect order effects in conjunction or in assessing evidence. The question, though, remains, if we want to use a formal probabilistic approach to decision making, how do we incorporate these order effects in a kind of natural way, that is without having to rely on heuristics? Okay, so the order effects is, as I said, especially for medical diagnosis, actually there are similar results for legal decision making. And again, if you're an AI researcher, you think expert systems in medical diagnosis, expert systems in legal decision making, right? Whatever is the basis for these expert systems, we of course have a very high expectation for consistency with some normative framework. I mean, we don't, it's one thing to ask whatever it is people are doing when they are responding to the Gallup poll, quite another to ask, what do we expect of doctors or lawyers or jury members when they're assessing evidence in relation to a high stakes situation? So, of course, the objective might be to train doctors to reach decisions that are as correct in some way, or to train judges or, say, lawyers or solicitors or jury members to reach, again, sort of quote unquote correct decisions in some way. So the motivation, all this kind of like apparent paradoxes appear incorrect and appear to go against intuition about what should be the formal foundation of probabilistic inference. So, I mean, if you take any person with a quantitative background in probability theory or maths or simple maths, you know, the conjunction fallacy or order effects appear incorrect in the way that something like 1 + 1 + 1 is 3 is incorrect. I mean, they appear mistakes, and there's no escaping this fact. So can human intuition differ in such shocking ways from classical expectation? And are humans irrational? And is maybe Bayesian theory not the right way to try to build artificial systems, or systems which aim to mimic human cognition? Now, the way I got into the research I'm about to describe to you is essentially the answer to the question: if we relax our focus on classical probability theory, is there an alternative perspective for correctness regarding these decisions? That is there an alternative way to understand what's normative or rational in these situations with the conjunction fallacy or question order effects other than classical probability theory? So that kind of links us to quantum theory. So, I mean, you're computer scientists, most of you are computer scientists, right? And obviously, when you hear the word quantum, what you may immediately think of is quantum mechanics. Now, quantum mechanics, of course, is theory of physics, and it goes hand in hand with all sorts of weird assumptions about the structure of microscopic physical systems. We're not interested in any of that. Essentially, we just look at the probability rules in quantum theory. Now, these rules are essentially a system for assigning probabilities to events, which is alternative to classical probability theory. In fact, if you look at something like the law of total probability in classical theory and say in quantum theory, the only difference is that in quantum theory you end up having an interference term. And in fact, there is a whole hierarchy of different probability theories, which basically differ in terms of the complexity of this interference term. So classical theory is at the base of this hierarchy, with interference terms being 0. Quantum theory is the simplest interference term in the sense that it involves two-way interference. And then you have additional steps, additional members in this hierarchy that involve progressively more complex interference terms. The point is, if we're interested in understanding decision-making as psychologists, or if we're interested in building artificial systems which are intelligent as computer scientists or cognitive scientists, then there's no reason to restrict ourselves to classical probability theory. You know, we can just look at the probability rules of in quantum theory and simply assume that, and simply explore rather than assume, simply explore whether, you know, we may have some gains in inference, even if the underlying implementation of these quantum probability rules is entirely classical. So most of us, all of us, as far as I know, we assume that the brain is fully classical. We just assume that phenomenologically, it may look like the mind follows sometimes quantum principles or quantum rules, because, as I'll try to argue to you, these are more efficient in certain cases. Okay, so I mean, I don't know how much you're familiar with quantum theory. I assume you're a little bit familiar with some of the ideas. So I'll just offer a quick and easy introduction to some of the key concepts, as these are relevant to what I'm trying to argue for. So with a quantum model for probabilistic inference, instead of having probabilities represented as subsets in a sample space, you have probability information represented in subspaces in a multidimensional vector space. It's basically called the Hilbert space. Just a vector space, complex vector space with various convergence properties. We can represent the relevant system with a vector in that space, or with a density matrix if you want. And in the context of the conjunction fallacy, for example, this vector would be the mental state of a participant after reading the Linda story. Now let's look at how questions and question outcomes are represented. So each question outcome in a classical space is a subset in the sample space, right? For example, the question outcome, rolling a die will reveal a 6, is a subset of all possible outcomes from rolling a die, right? That's trivial. And the quantum approach is that each question outcome is a subspace in the overall vector space. And the main operation we're interested in is that of projection. So we take a vector and we project it, we lay it down onto the relevant subspace. For example, suppose we got a two-dimensional subspace representing possibility A, and this is our state vector. Then the projection of the state vector onto the space is just a solid blue line. Again, I'm kind of assuming you're mostly familiar with all this stuff, just perhaps in different contexts. So I'm kind of rushing ahead a little bit. But, well, if there are any questions, please just text me or tell me or interrupt. So in quantum theory, the way people associate probabilities to subspaces is a squared magnitude of projections. So it's kind of interesting that if you basically have your events lattice is subspaces, the only way to consistently associate probabilities to subspaces is using this quantum rule. That is basically by taking the squared magnitude of projections. And all we do is that the probability, for example, that I'm thinking about possibility A would just be the squared length of this projection. The main difference, well, I mean, the couple of differences, but I guess the main difference between classical theory and quantum theory is that in classical theory, all questions are compatible, which means that I can take any combination of questions, potentially all questions in my knowledge base, and I can always construct a joint probability distribution. Now, this is important. I may not need this joint probability distribution, right? I may not need to know whether Linda is a bank teller and a feminist and has black shoes and say lives in a flat and blah, blah, blah. I may not need it. But this joint probability distribution always exists. And in fact, the joint probability distribution is arguably the basis for Bayesian probabilistic inference, because once you have the joint, you can compute any marginal or any basically logical combination of marginals from this complete joint. Now, in quantum theory, you can have some questions that's compatible, right? But some questions are incompatible. And now that is kind of like the crux of why we think that quantum theory is a good approximation to Bayesian theory when it comes to agents which have finite resources. Incompatibility basically means that we can't have a joint probability distribution, and certainty for one question creates uncertainty for another incompatible question. If you've done quantum mechanics at any point in your lives, the classic example is position and momentum. These are incompatible observables, which means that certainty about position induces sort of creates uncertainty for position and vice versa. And of course, in physics, this has created endless debate about the structure of reality, right? You know, does something have position or does it not? But in the context of probabilistic inference, that is a much simpler idea. It's just the idea that if I have two questions which are incompatible, just asking one question makes me uncertain or changes my perspective about the subsequent question. And this could be because asking the question disturbs the system of interest. So I'll show you an example later on of exactly how down to earth all these ideas can become. Now, the use of incompatible questions. The use of incompatible questions basically means that when it comes to conjunction, I can't have a classic conjunction of concurrent evaluation. So in classical conjunction, it doesn't matter whether I evaluate feminist or bank teller first, right? You know, you basically just pick out a particular basis vector in your classical vector space representation, right? It's a concurrent operation. But of course, if you employ these quantum probabilities, then you need to evaluate one question and then the other, because obviously just evaluating the first will create uncertainty for the second. By the time you've reached the second, you've got uncertainty for the first, right? So, you know, you need a sequential operation. Now, the point that you can't evaluate incompatible questions concurrently, is essentially the key point that gets us to why quantum theory can offer a simplification for in relation to classical theory. Now, in classical theory, you basically have a space of all your questions together. There's no, you can take any combination of these questions. You can have a joint probability distribution. You must have a joint probability distribution. With quantum theory, instead of having like a big space of questions, you basically have smaller spaces of compatible questions. Now, within each space, everything's classical, right? But if you go across spaces, then you basically have these uncertainty relations. You can't. If you take like one space of compatible questions here and one space over there, you can't evaluate pairs of questions concurrently. So the difference is between having a Boolean algebra, which is the logical foundation for classical probability theory, and the partial Boolean algebra. Now, partial Boolean algebra is basically a set of lots of little Boolean algebras arranged in such a way that there is consistency where they overlap. But look further out, and you got these uncertainty relations. And just kind of like offer an example, which of how we understand these things, right? So let's take Brexit. A lot of people have read a lot about Brexit, but different people, depending on the background, will have like different biases. So, for example, let's take, say, John, who may be a finance expert and know an awful lot about Brexit in relation to finance implications, right? But he also knows that Brexit may have implications, for example, about the environment. But John doesn't have the time or the resources to actually integrate his representation for finance with his representation for the environment. It's like a partial Boolean algebra. You've got a set of questions concerning finance, right? And you're kind of expert in these questions. You're fully classical in this subset of questions, right? You've got a separate set of questions regarding the environment, right? And again, you're kind of, let's say our John example is, he's interested about the environment, so he knows a lot about the environment as well. But he doesn't usually consider questions from finance with questions from environment. So you're fully Bayesian and rational here, fully Bayesian and rational there. But if you try to go across, then you have uncertainty relations. Now, you can work out, we've done that, you can work out the information cost of having a big Boolean algebra of all your questions versus just having these subsets of questions where you are rational, you're Bayesian within each subset, but not across subsets. And actually, we think the information cost reduces dramatically, exponentially so. This is not to say that there aren't other ways to reduce information cost. So remember early on I told you that a very popular way to simplify Bayesian representations is to employ sampling approximations. Since we've been talking a lot about complicated joint probability distributions and conjunctions over here, well, it's time to tell you that, well, obviously, as you almost certainly know, another very common way to simplify complicated probability distributions by using Bayesian networks. So instead of having like a conditional probability with like a million terms, you base your reasoning on a simple Bayes net, and your conditional dependencies become a lot shorter. So as far as we can tell, the simplification you get from using quantum representations is equivalent to that from using Bayesian networks. But the important thing is that it looks that, at least in some cases, humans actually employ these quantum representations. So I'll just demonstrate this shortly, like in the next slide. So essentially where we are is, Bayesian theory, we love it, right? It's just in its full version. Obviously, it's not fit for purpose in any practical application. Different ways to simplify. You can look at sample approximations. You can look at Bayesian networks, right? These are kind of the established approaches. The sample approximation is more so in psychology. Bayesian networks, I imagine, in your area. We come along and say, well, there's a third way. You can use these quantum representations. You get a lot of simplification. The price you pay is that you end up with uncertainty relations that may not exist in real life. So anyway, that was kind of like essentially the main take-home message concerning how we think these ideas might be relevant in AI. So let me just kind of like complete now and tell you how we model conjunction fallacy, and also give you one or two quick examples of situations where you might have this apparent incompatibility, even for observables, for questions which are macroscopic. Okay, so the quantum analog to classical conjunction for compatible questions is basically to just have a sequential operation. So instead of having probability A and then B, you model instead probability A and B, you model probability A and then B. And in terms of these quantum rules, this sequential conjunction decomposes to a marginal times a conditional. Okay, so just a simple example of how this would work in practice. So let's assume we have a simple one-dimensional subspaces. We start for the representation concerning the possibilities that Linda is a bank teller and not a bank teller. And we have a mental state which is very close to the not bank teller subspace, because by assumption, when participants read the Linda story, it's assumed that they think it's unlikely she's a bank teller. And then the probability given where we are over here, the probability that Linda is a bank teller is this square length projection. It's very low by assumption, right? This is how Linda was described to participants. Now let's throw in a basis set for feminism. Now, the way I place that is that the way to place this, in a two-dimensional space, it's simple. In a three-dimensional space, it's more complicated. And actually, if you're tempted to employ some of these for an actual AI system, there are some issues I'm happy to discuss. But in 2 dimensions, things are very simple, because all you've got to do is ask yourself, if I consider prototypical feminist, that is, if my state vector is along the feminist array, then how likely do I want to call such a person a bank teller versus not bank teller? And here, we just place it in such a way where we assume it's neither too likely nor too unlikely, kind of halfway. Also notice that the state vector is very close to our feminist array as well. Again, by assumption, Linda is a very likely feminist. Okay, so given where we are, the sequential conjunction is just a sequential projection where you project first on the feminist and then the bank teller. And that's the, according to quantum rules, the probability of feminist and then bank teller. The probability of the marginal is direct projection. And if anything else, hopefully this convinces you that with this quantum rules probability, you have a situation where the conjunction can be considered more likely than the marginal. That's the essential point. As long as we can understand the questions feminist and bank teller as incompatible, that representation gives us a scheme where it's no longer incorrect to say that this probability is higher than the marginal. I'm going to skip a couple of things because I believe I've got only 3 minutes left, and I just wanted to give you an example. So I'm going to skip all that. I'm going to skip all that. I'm going to skip all that. I'm going to apologies for the little, just going through this quickly. And I'd just like to show you this example. That's an example of a macroscopic system where it might make sense to treat the corresponding questions as incompatible, as contextual. So let's say that your parents, right, and you've got a baby girl, baby Eve, and she loves sleeping on her front. Now, the question the parents are interested in is Eve sleeping on her back at 10 p.m. and 11 p.m., right? Which is kind of like parents with a newborn baby, you might be inclined to just kind of be, doing this sort of thing. Now, whenever you check, you can check on Eve, but when you do, this disturbs her and she rolls over. So what we've got here is a probability that the position is back is very low, right? Because we said she likes sleeping on her throne. So 0.1, same as probability of sleeping on the back at 11 o'clock. So position at 10 on back is the same as position at 11 on back, and it's very low. However, if you check at the position at 10 and then at 11, the probability that she's now sleeping on her back at 11 is much higher because, remember, once we've checked on her at 10, she's likely to have rolled over. Now, a reasonable question here is, why is that not different from conditional probabilities? There is an answer, but I'm going to reserve that for questions if you're interested. Instead, I want to show you this diagram. So here we've got a sample space where we check on both times. So in 30 days, right? Say her parents are obsessed and check on Eve every day. Now, if they check on both occasions, she's most likely to be sleeping on her front, right? But it's a bit more likely that she's sleeping on her back at 11 o'clock, simply because, as we said, she gets disturbed. Whereas if they just check what's happening at 11 o'clock without checking previously, she's very unlikely to be sleeping on her back at 11 o'clock. So we separate the sample space, which goes back to this idea of having like a partial Boolean algebra. We've got one situation, it's not quite equivalent, but it's similar. We've got one sample space for when we check on Eve both times and disturb her, another sample space when we don't. And it's like the back with checks, if it's just more likely to be sleeping on her back after a check. Now, the essential point, and I'll finish with that, is that you can organize both events in a single sample space so that you can ignore this distinction. If you do, you no longer get the conjunction fallacy, but you miss structure. If you keep things separate like this, so if you compare this frequency with that one, it may look like it's the conjunction fallacy, but of course it's not a real conjunction fallacy because you just separate out sample spaces. Now, this separation can be done classically as well by conditionalizing, right? But of course, the advantage of using these quantum presentations is that there are special rules for relating representations in one sample space to another, with geometry transformations and everything. So let me just kind of like finish because, because I've run out of my time. And the essential points I want to make are that, as I'm sure is the case in some, at least, circles of AI, people really love Bayesian inference, right? And believe that however we end up understanding human intelligence, part of it is going to be Bayesian inference. But, there are a lot of very surprising discrepancies between Bayesian inference and what people are doing. The point of our research program is to basically explore whether these discrepancies may be understandable by employing these quantum probabilities. There is a chat. Let me see if there's a question. All right, 5 minutes left. All right, thanks. So anyway, so I'll finish with that. Thanks for your attention. More than happy to answer any questions you might have.
Thank you, Emmanuel. That was very informative. So the floor is now open for questions.
Hi, I have a question. So to summarize, it seems like, please correct me if I'm wrong about this, it seems like the reason that you want to use quantum probability is essentially because the measurement, doing some sort of measurement, can affect the brain state, and therefore future measurements might be affected. In the same way as there's like mode collapse when you measure stuff in...
Yes, okay. But I wouldn't say brain state because we don't believe this goes down to the brain. I mean, we think everything at the neurophysiological level is classical. So yes, the question is, I guess there are a couple of motivations. One is exactly what you said. We want to capture in more formal terms the idea that when you have a sequence of questions, asking one may disturb your system or may create mindsets or perspectives that are unique for the other one. The other motivation is that if you use these quantum rules, you seem to get good models for some of these findings which are puzzling from a classical perspective. And the third motivation is one of bounded rationality. That, you know, I mean, we know full Bayesian inference is not tractable. And the question is, what's the most sensible way of trying to do something that looks a bit like Bayesian inference, but it's basically limited in a realistic way?
Okay. So my question was, have you considered this same have you considered that maybe the quantum probabilities could fall out from a continual learning approach? So for example, if you're asking a question A and then a question B, and you ask the question A and then that changes the state, and the state then learns because it's got new information or any sort of information, now the state's a different state. So when you ask B, it's now going to give a different answer because it's in a different state.
It's interesting, and we don't know.
Okay.
So I guess in a fantasy world, you know, one might basically try to use to basically start with Bayesian theory, right, and use perhaps reinforcement learning with some cost for complexity, and maybe predict that, you know, when the system encounters costs that are too high, something like quantum theory falls out. I don't know. I mean, the thing is, it's still a fairly new research program. So it's been going on for about 10, 15 years, right? And I think the biggest challenge, basically, is that people don't really understand where incompatibility comes from, which is your question. Yeah. So why is it the case that feminism and bank teller appear to be incompatible for Linda? We're not entirely sure. I mean, the best answer is that this has to do with resource limitations, right? You know, we just not used. So it's basically a frequency approach. So we don't often consider questions about feminism together with questions about being a bank teller. So, you know, when they come together, we haven't got this joint probability distribution, we haven't got this classical space. But how to use, for example, frequency or learning to predict kind of like a smooth transition from full incompatibility to full compatibility, I don't know. But that is a key question. That is essentially the most important question we're trying to solve. And when I say we try to solve, is we hope somebody will solve for us, because I'm not sure we're clever enough to do it ourselves.
So yeah, that was the thing that, so when I was sort of listening to the talk and I sort of thought about this sort of continual learning like approach, so my sort of explanation for that sort of thing would maybe be something along the lines of your the change which has happened. You could get different, so when you get certain information, maybe whatever mechanism you have which is doing this sort of learning inference engine, learning whatever thing you're using, might not change the whole sort of manifold of where your states are, your whole space, and it might only affect certain parts, which, and then you get these sort of it looks like disjoint subspaces where if you ask one question on something completely unrelated, then the second question, that'll affect one part of the vector, and therefore it's not going to make a difference.
Yes.
So that, do you see what I'm saying?
Right. So the metaphor of using subspaces is generally speaking appealing to psychologists in ways that have nothing to do with quantum theory, right?
Yeah,
For example, when it comes to similarity relations, and I imagine that's something of interest to AI people as well. You know, sometimes in models, people propose that, you know, when you have got like a super complicated conceptual space with all your stimuli, but say you're only interested in animals, you basically project into a subspace with animals and you compute your similarities in that subspace. Now in quantum theory, I mean, that's natural in quantum theory as well. You can imagine like a tensor product space of all your more individual spaces, right? It's all classical so far. But like, you know, in most of our reasoning, we just ignore most of them. Now, it's got to be said, it's, I mean, there are a lot of unanswered questions, though. I mean, I think I agree with the general idea. Let me just say, we completely agree with the general idea that, you know, being able to show how, in some smooth way, you end up from incompatible representations to compatible ones would be a major step in that research program. Yeah, and so, but do you personally, from what you've seen, think that it's likely that it's just some sort of quantum system, or it is some sort of classical system where, at an approximation, the quantum stuff falls out? It looks like. I say, so what I believe is happening is that we do develop small Bayesian spaces for limited sets of questions we are very familiar with and we are very expert in. But it just, the human mind is a complicated beast, right? We've got got millions and millions of different themes we're interested in, and we just don't integrate these small themes with each other. Now, if I were trying to build a robot, right, with an AI system in it, I would imagine it makes sense to compartmentalize questions in the same way. So, for example, the robot has one set of compatible questions for what you do in the house, and a separate one for what you do, say, when it's out in the garden, right? But it would just seem to me too expensive to try to integrate these two sets of questions together. And whatever happens, I mean, the thing about quantum theory is that it basically, once you have a set of relations in one space, it kind of lets you, to some extent, keep this separate for whatever happens in another space.
Yeah. Interesting. Yeah, I find this really interesting. My undergraduate was in physics, so.
Yeah, the law of X physics. My background was in physics too.
I think all the best people's are.
Yeah. Thanks.
Yeah, thank you.
Okay, we have about 5 minutes left. So any more questions?
Muted. Sorry, I was muted. Do you think that the assumption of rationality by itself can be too strong?
All right, Esther, look, okay, so fine. So the assumption that an average human agent or an average, say, AI agent is rational may be too strong, right? But even if that's the case, there will be circumstances when we want our reasoning system, whether it's artificial or human, to be as rational as possible. So if there are basically strong discrepancies between whatever our decision system is doing and expectation, then we need to understand them, and we need to understand how they come from. And one answer from all this is that maybe there will be situations where questions just disturb the system, in which case it might be rational to have conjunction fallacies. I guess the other answer is that, okay, I think at least in decision theory, people are giving up on the idea that people are rational in some kind of Platonic way, right? That is, they're rational in the sense of full Bayesian probability theory. But it also seems implausible that we're how to put that? It also seems plausible that we are rational to some extent. And that comes up actually more so in the animal behavior literature than in the human literature, because animal behavior people would say, well, if your species, whether it's pigeons or squirrels or whatever, were not rational in terms of how they estimate probabilities about foraging, about mates, about predation risk, they'll be dead. So, the animal behavior people, I think, make the case for some form of bounded rationality a lot more directly than decision theorists can do it. Because from a decision theorist point of view, well, whether people reason correctly about Linda, it's kind of neither here nor there, right? It just seems too abstract to be of direct relevance to our survival. So to answer you, I believe the human mind tries to approximate Bayesian rationality. The question is how it does it. And the hope is that if we can extract the principles with which the mind does it, maybe this would be a good guide for AI systems as well.
Yeah, I agree to a certain degree, but I think that some of the examples that you have put here can be easily or fairly easily explained from a bottom-up perspective, like associative learning.
They might, absolutely. Yes, and people offer all sorts of explanations for these so-called paradoxes, right? In terms of models which have nothing to do with probability theory. So forget about probability theory. We look at, say, heuristics like representativeness or similarity, something like that. And these heuristics are more easily explainable in terms of associative learning. I have no answer to that. Well, I have some answers, but I have no definitive answer that will, unequivocally convince you. So one answer is that the associative learning, arguably, and I understand it's a big argument, does not get us close to this idea of rationality. And humans like to think that some part of our minds is rational, and that's, in Bayesian terms, rationality can be sort of explained in very concrete formal terms, right? Associative learning, less so. And the other answer is that you can. So associative learning is a complicated argument. So I'm not going to go into this because associative learning, whatever else the human mind is doing, it's also doing associative learning, right? So nobody contests that. So I'm not, the question is whether there's a place in understanding the human mind based on Bayesian inference as well. So I'm leaving associative learning aside, but when it comes to heuristic explanations for these paradoxes, there is a slight problem in the sense that many of these explanations are actually too fragmented to enable a coherent understanding of intelligence. So yeah, I don't know about associative learning. I mean, I think that's a valid point. I mean, I think ideally you'd have a model of cognition or inference that has a component of associative learning, and from that, on some metrics of I guess rationality or good decision making, you end up with something that looks like Bayesian inference as well. But it's you do have in psychology literature, actually Eduardo probably knows this as well, because he's published in the psychology literature on associative learning. There's a massive disconnect between this tradition. So you've got a large group of people like myself who are interested in probabilistic inference, and know inside out all these kind of sample approximations or whatever. And then you have the associative learning people, and they don't really talk to each other very much. And I don't know how the two relate to each other. I mean, I think that's extremely important. It's not where we are. So I can't answer you. Yes, you're right. It may be.
No, I agree with you completely. I'm from the area of associative learning, and well, I believe there are some people around from Bayesian perspective that can interact with associative learners. I don't know, Daniel Navarro, for instance. And anyway, I think, yeah, I agree with you. We are completely separated point of view, top down, up down, bottom up, and perhaps integration is the key.
Yeah, well, but I mean, yeah, I know, but I mean, I think for behavioral sciences specifically, I think there are a few examples where the need for integration would be potentially as landscape altering as this one, like between probability theory proper and associative learning.
All right, thank you very much.
Okay, I guess we have time for one more question.
Okay, this is not a question actually. Hi, Emmanuel. Again, rather a final comment, if I may. Okay, it's about from the artificial intelligence point of view. I don't know if I would actually like to to use artificial intelligence to replicate natural bias. Okay, or if I may. Or if actually, as a software developer, I would actually like an artificial intelligence to be able to give me the right answer to the Swedish people problem. For example, in a rich environment.
You may have an expert system. You may have an expert system which is meant to aid medical decision making, right? And in such a case, you would want to be rational. In terms of artificial intelligence, right? Can I just say one more thing about these quantum representations? Because I mean, I don't want to do more work on AI because for various reasons. But so you think of memory, right? If you have an artificial agent, it makes sense to have memory, whatever happens, and humans too, obviously, right? But of course, if you take any given instant, say in our daily cycle, then right now, for example, right, there are just millions of these happening. Obviously, I'm talking to you, and I'm looking at my computer screen, and there are some cars outside, and if you basically try to create an atomic representation of what you encode at each given time, you end up with millions and millions of possible pieces of information. So Eduardo, you've forgotten about this, but actually, about a year and a half ago, you recommended to me this introductory AI book by, I don't remember this, the Introduction to AI, this kind of standard textbook.
Yeah.
And And you know, a lot of this one, no, not this one, and a lot of the paradigms there are based on a lot of the paradigms there are based on there we are.
Yeah.
A lot of the paradigms there are based on predicate representations, which very quickly become intractable. Now, the advantage with quantum representations is you basically take a snapshot of each instant, which is your superposition state, and that can be then queried flexibly in whatever basis you want. So maybe I'm not explicitly encoding, you know, whether I'm hot or cold right now, but I've got a snapshot of my state, and then later on I can try to think, was I hot or not? And then you know, I can make this query in my mental state. And of course, the price you pay on that is that every time you query your superposition, you have to collapse it somewhere, so you change it.
Yep.
But it does offer. I mean, we think so. We're doing work on temporal Bell inequalities now, and it looks to me that the only paradigm that makes sense for a bounded agent in terms of memory is something that looks like quantum states.
No, I agree. I mean, it was not a critical comment at all, Emmanuel.
It's all right. I didn't take it as critical. I just used as an excuse to make this additional point.
No. I said, as you know, I have followed your work, and I think it's a very, you know, interesting approach precisely to the problem of tractability in the, you know, simulation of cognitive processes. I do love it. No.
Okay. Well, thanks. I mean, you know, it's well, thank you.